12th lecture of ISSE webinar series, and we have completed all 1 year today. We are completing 1 year today, and you all know that ISSE, that is Indian Society of Structural Engineers, is a 30 years old organization which is meant for civil and structural engineers, and it was started by late Shri R.L. Nene sir, uh, with the vision that the institute will gather all similar minded people or co-professionals together, and we can put our opinions or any observations in front of government bodies. Then whether there are any issues, then we can do any webinars, seminars. Then ISSE has published so many books, booklets, and reports. ISSE has also arranged so many site visits, and ISSE has got 3,000 plus members. And there are several student chapters. And basically, this, yeah, volume is too low. Someone is saying, I think my volume is full. Okay, so basically this session was started to help students, and now we found that the activity was becoming so popular that many professionals have also started joining this activity. So I once again welcome you all to this 12th lecture of ISSE student chapters. To know more about ISSE activities, publications of ISSE, and to get the membership of ISSE, you can log into ISSE website, that is www.issc.org.in, and you will find all the details are given there. And the membership can be taken fully online. You need not to come to ISSE office or something. You may be anywhere in India or outside. You can fill in the form, you can deposit the fees online, and submit the documents. So that's it. So this is about ISSE, and this is about the activity. Now let me introduce you with our today's speaker, Shri Debasis Barman sir. So yeah, so Debasis sir has completed. He has a huge experience in geotechnical and tunneling aspects. So sir completed his graduation from North Bengal University in 1997. After that, in 1999, he completed his post-graduation in soil mechanics and foundation engineering from Jadavpur University, Kolkata. From there, he started his professional career and worked with CES for about 2 years, NHPC for 5 years, SMEC for 1.5 years, Scott Wilson for 3.5 years. And during these engagements, he worked on various interesting projects and hydroelectric works, where he could do the analysis using FEA software, then slope stability analysis using SWET software. Then he was also involved in London Crossrail project, where he used FEA and Plaxis softwares. After rigorous 13 years experience, he felt that after 13 years of work with consulting company, he joined EPC construction companies in India like Gammon, and then thereafter Afcon's infrastructure, where he got an opportunity to work on Chennai Metro rail underground rail project and India's first underwater tunnel project in Kolkata from Howrah Maidan to Mohakaran station. Back to 2014, he resumed back to consulting profession, and where he worked with Seastar, GeoConsult, Amberg, and Bechtel. Apart from Chennai Metro, Kolkata Metro, London Crossrail, he also worked on a couple of interesting projects like USB, Udhampur, Srinagar, Baramulla rail project, Ahmedabad Mega Metro project, Lucknow Metro project, Subansiri Lower Hydroelectric project, Srinagar Hydroelectric project. And he acquired a unique blend of NATM and TBM tunneling method in his professional career. So I think we should get the benefit out of his experience in today's lecture. So I would request you to ask many questions to him relevant to topic, of course, of tunneling. Since past 1 year or so, Sir has started his professional service in New Delhi and acting as a consultant. And he helps contractors in DPR preparation, technical audits for the road tunnels, and mentoring and technical training to the juniors to improve their tunnel design skills. He was a member of ICI, that is Institute of Civil Engineers London. He is a fellow of IEI, member of Engineering Council, and a few more other professional bodies. You can find many informative documents prepared by Sir on his LinkedIn profile, like RMR rating, rock mass rating, or say tunnel phase stabilization, convergence confident method, including ground relaxation, then geotechnical investigation for underground structures and tunnels, etc. So now, without further, any delay, I welcome him to start his presentation on precast tunnel segment and underground metro projects, design and construction aspects. So over to you, sir. You can. I will present your
Yes.
presentation. I've started. So then you can start speaking. So I'm just sharing the presentation. So whenever you are done with the first slide, you say next. I will
Yeah, yeah.
navigate next slide. All are requested to ask the questions in the chat box. Please take the full. Yeah, is the slide visible to everyone?
No, no. Yeah, yeah. Can you make it full screen?
Yeah, it is full screen.
Okay, okay. Okay, good
Yeah.
morning to all. Yeah, good morning to all, and thank you for your expressing the interest to for this topic. In fact, Mr. Vivek was my ex-colleague in AFCONS. We have worked in AFCONS. He was also part of the metro project, and he requested me to present this topic because this topic was one of my topic in past webinar. I presented to around 15-20 people, and then I posted in LinkedIn, and he got interested. Am I audible?
Yes, sir.
Okay. So today topic is TBM precast segment design principles. But before going to the precast segment design principles, I will clear you on the topic of the TBM and what are the components of the segment. Now, TBM precast segment is quite different from the normal cast in situ liner that you find in NATM tunnels, that where we are making a telescopic gantry and then we are putting the shuttering and then we are putting reinforcement and then we are casting the liner. TBM segments are quite different from a cast in situ liner. Here, the segments are casted in the factory. There is a precast factory setup made. Even it is a metro project, it is a road tunnel project, it is a water tunnel project. Any project, a precast segment factory has been set up where we are producing lakhs of tons of steel segments in the 1 month because every day, depending on the TBM, depending on the ground, it approximately comes if it is a very soft ground in a metro project. Normally, you can 10 to 15, sometimes 20 segments are being erected in the tunnel. Now, this segment, after being casted, they're transported it to the tunnel side, then they are lowered in the shaft, and then they are taken inside the TBM by a wagon. And then in the TBM, there are uh,
Uh,
can you please
Participants,
mute?
please keep mute. Mayurji, please mute the participant.
And then these segments are being erected by the TBM robotic arm. And these segments are not a continuous lining. It's a piece of different part that makes a complete circle. So normally in metros we are using 5+1. So 5 means the normal segments 5 part and 1 is the key part. So it can vary. So it can be 5+1, it can be 6+1, it can be 7+1, 8+1, depending on the tunnel diameter and the configuration of the tunnel. Now we will first focus on the what is the basics of the TBA. Okay, next slide, please. Okay, so first part is the tunnel boring machine. The TBM is the tunnel boring machine. So there are two types of TBM. One is called the soil TBM or soft ground TBM. Another is called the rock TBM. Rock TBM is mostly used in the very hard rock. Suppose in Pune, in Mumbai, And some in several hydroelectric projects also we have used. In Kishan Ganga project we have used a double shield TBM. There was a TBM working in the Joshimath hydroelectric project, but it got stuck and finally it could not be retrieved. But normally in hard rock, we are using three types of TBM. One is called the open TBM, one is called the shield TBM. Open TBM means that this type of TBM does not needs any phase pressure. Phase pressure means when the TBM is moving, there is a whatever the ground that is ahead of the TBM then needs to be stabilized. But due to the very hard rock, so there is already the ground is so hard, so it has a automatic. It is a very high stand-up time, so the ground ahead of the TBM will not collapse. So we can go with the open TBM, or where we are finding a very stable wall or stable face of the ground. In the shield TBM, there are two types of TBM. One is called double shield TBM, another is called single shield TBM. The difference between the double shield and the single shield TBM is in the single shield TBM, whenever you are excavating, then you cannot install the segment at a parallel. So you have to excavate, then you have to install the segment because the ground is very weak and there is a water flow ingress. So a single shield cannot do both the operation. So the process is quite slow. In a single shield TBM, the daily progress rate, if you compare to a double shield TBM, the progress is quite low. And we are mostly using it's a very uh, low quality rock or very not very soft but not very hard rock also. And if it is a very hard rock condition, then we are using a double shield TBM with gripper. Now the main function of the TBM is whenever the TBM is moving, it is taking the thrust from the segments. The segments are erected behind the TBM, and TBM whenever it is moving, it is putting the jacks on the segment and then it is moving. But in double shield TBM with gripper, it is putting the gripper on the side walls. So it is not putting the thrust on the segments, rather it is putting the gripper on the side wall and then putting the thrust and it is moving. So there is a dual operation. The TBM can move and the TBM can build the segment. So there are two types of shield in the double shield TBM. Double shield TBM we are using mostly if it is a very hard rock condition where the chances of the collapse of the rock is very low, and there is a very favorable ground conditions, then we are using a double shield TBM. Now, if I go to the soft ground, there are mostly two types of TBM. One is called arc pressure balance machine that is mostly used 90% in all type of metro projects, whether it is Delhi Metro, Agra Metro, Pune Metro, Mumbai Metro, Lucknow Metro, everywhere you can find, even Calcutta Metro also we have used arc pressure balance machine. Arc pressure balance machine means that whatever the earth that is being excavated by the machine, that earth is being used to stabilize the face. So you are using the excavated material to stabilize the face ahead of the TBM. So that is why it is called a earth pressure balance machine. The earth pressure balance machine is mostly used in a clay type of soil, cohesive soil, mostly where the silt and clay fractions are very higher. So we can have a high shear strength. So the ground can be stable due to the shear strength that we are using the earth pressure balance machine. Slurry machine is mostly used in a cohesion-less soil, that is sandy type of soil, or where if you take a silty sand concept, where the sand content is very higher, we are using slurry type of machine. Slurry type machine mostly used in Bangalore and Chennai because here you will find a mixed ground concept. Rather in Delhi, Ahmedabad, Lucknow, you find mostly the cohesive part is very higher. If you go to the Mumbai or Pune part, you find the rock, but that is also a mixed part of the rock. But in Chennai or Bangalore, due to the coastal areas, you find a very high content of cohesionless soil. So you are using slurry machines, and the slurry machines here you are pumping the slurry ahead of the TBM, and that slurry is forming a mud cake on the ground face, and that is stabilizing the ground. So this is the two types of machine: the earth pressure balance machine and the slurry machine. Nowadays we are finding lots of areas where you are getting very high type of mixed grounds where we are getting sometimes at the crown part a very hard rock, at the bottom part of the tunnel a soft rock. So it happens that we cannot use either earth pressure balance machine or we cannot use slurry machine. So we are making a combination of both type of machine, so that is called a hybrid machine. So hybrid machine, they have a function of both EPB slurry or sometimes EPB with rock, sometimes slurry with rock. So the transition can be made automatic. So suppose if I use a earth pressure balance machine and after 350 meter I found a very hard rock condition where the EPB machine cannot cut the rock, then I have to change my mode of operation or the mode of transition. So if I wait to make this transition, it will take a long time, and I cannot park the TBM for a long time because it is a operational difficulty. It will attract lots of settlement in the ground also. So we are using a hybrid machine where the automatic transitions can be made, but these hybrid machines are very costly. So it depends on the if your type of the ground and if you can justify your client that this machine is really required, and if it is a very long tunnel, then we are mostly using this hybrid machine. So this is the overall machines that we are currently using in the tunneling industry across the global market. If you okay, next slide, please. Okay, now we come to the soil TBM types and how it is operating. Okay, now if you there is a graph, or you can take there is a chart where the machine type of the machine depends on the permeability of the ground. So as I told you earlier, the slurry machines are mostly used for a cohesionless soil where the permeability is very high, where the chances of the water ingress to the machine or through the ground is very high. You are using a slurry machine. So in the slurry machine, what we are doing, we are pumping a bentonite slurry. Sometimes we are pumping a cement bentonite slurry, depending on the permeability of the ground. And that slurry is forming an impermeable layer on the ground ahead of the TBM. So the ground can be stable, because if the ground is not stable ahead of the TBM, then what happens? The ground will try to flow inside the TBM, and that will cause a problem, because the TBM inside the TBM, we are not allowing the ground to flow or not allowing the groundwater to come inside. So mostly in a highly permeable soil, you are using the slurry TBM. So in Chennai, in Bangalore regions, we are mostly depending on the slurry TBM. Currently also in Bangalore Metro, L&T or AFCONS, they're using a slurry TBM. EPB machines are mostly used in the cohesionless soil, a cohesive soil where the clay fractions or the cohesive fractions are very higher. So silty clay, where the permeability is very less. So 10 to the power minus 7 meter per second, 10 to the power minus 8 meter. So it has a very high shear strength. So it has a very high cohesive part is very higher. So the ground can stand, because after even the TBM is cutting the soil mass, the ground will not collapse due to the shear strength or due to the cohesive nature of the ground. And here there are very less chances of the water to flow through the particle of the soil because the permeability is also low. So we are using the EPB machine. Now EPB machine, what you are using, there is an excavation chamber where the excavated mass is being stored temporarily. Now this excavated mass, whatever the thrust that is applying onto the ground face, that is used to stabilize the TBM face. Now, how much mass I will extract from the excavation chamber? How much mass I will put on the excavation chamber? That depends on the scenario. That depends on the whatever the thrust I'm encountering from the ground. What is the type of the ground? If the ground has a very high clay content, if the ground has a very high seepage condition, if there is a low ground cover condition, there are different conditions. I keep the change my excavation chamber volume, the extracted mass, whatever I put the excavation chamber, I can switch on. So this depends mostly on the operational part. It's not a design part. So basically, EPB machine is a earth pressure balance machine where the earth, that is the ground ahead of the tunnel or ahead of the TBM, is being stabilized by the excavated mass. Okay. Now the next slide, please. Okay. So here you can see this is the this is a complete TBM part. So here you can see there is part one is the cutter head. Cutter head means that is the cutting of the mass. So the cutter head has teeth, and these teeth can have different type of strength depending on the type of the ground. If it is a soft clay, the teeth will be not more abrasive. If it is a very high rock condition of the ground, then the teeth becomes more abrasive. Then there is a thrust arm. Thrust arm is basically this arm is putting the thrust on the segment, and it is helps to move the TBM ahead. So mostly the TBM, you can heard that there is a jacks in the TBM, there is a ram in the TBM. So this is basically the ram of the TBM, which is putting the thrust on the segment, and then TBM is moving. Then there is a bentonite slurry feed. Bentonite slurry feed, as I told you earlier, in the slurry TBM, you are using the bentonite to stabilize the place. So there is a slurry or bentonite feed through which we are stabilizing the ground ahead of the TBM. Then there are segments. The segments means that is the lining part. So there are different parts of the segment that is being put behind the TBM. So there are, if you consider the TBM has a length of 18 to 20 meter, but if you see the whole TBM, it is approximately 180 to 200. That is the mostly the backup unit. But if you call up the TBM, that is comes around 15 to 18, sometimes it is 20 meter. Now the TBM, the front face is called the TBM shield, and the next part, the trailing part is called the tail shield. So there are one is the front shield and another is the tail shield. So from the tail shield end or the trailing end of the TBM or the edge of on the end of the TBM, we are feeding the segments. So as the TBM moves on, the segment is building continuously. So there is a gap between the TBM and the between the segment that is being erected, and that in between that gap, that segment TBM jacks, they are putting the thrust on the segment and then they are moving ahead. Then there are tail sealant. There is annulus grout that is mostly used to stabilize the gap between the TBM and the segment, because at the trailing edge of the TBM you can find there is a gap, that is the part number 6. If you can see, the TBM cutter head is slightly higher than the TBM segment dimension. So if you see, our finished tunnel dimension is 5.5 meter. Our TBM diameter, cutter head diameter, will be approximately 6.55 meter. So it is slightly higher than the TBM. TBM cutter head is higher than the segment dimension, and there is a gap at the trailing edge end. That gap depends on the TBM specification. Sometimes this gap can be 150 millimeters, sometimes this gap can be 200 millimeter, sometimes this gap can be 350 millimeter also. And this gap needs to be filled by grouting or by pea gravel or some sort of material. You need to fill the gap. If you don't fill the gap, what happens that that portion, the ground will try to move inside the TBM, and that causes the volume loss. So if you people who have worked in the metro project, they find a very common term called the volume loss. The volume loss means that the whatever the ground that is at the tail end of the TBM, and if that gap is not closed immediately after the segments are being installed, the ground tries to move inside the TBM, and that movement causes a settlement or a movement of the ground inside the TBM, that is called the volume loss. So volume loss is basically the movement of the ground in the trailing edge of the TBM, and that is expressed as a percentage. So more the volume loss, you can expect more the settlement of the ground, because whenever the ground is trying to move inside the TBM, that is also causing some settlement above the TBM also. So if the volume loss is 1%, 1.5%, you can expect a very high settlement. So it can be 20, it can be 35, 40 mm also of the ground. If the volume loss is very low, then the settlement is getting controlled. So our purpose is always, whenever we are installing the segments, we need to fill this gap, or you need to do the annulus grouting as soon as possible, so the volume loss can be controlled. The volume loss mostly occurs at the tail end of the TBM. In the ahead of the TBM, the volume loss part is very low. So in a metro project, we are always trying to keep the volume loss within 0.5%. And if you measure in practically, if you are doing a very good TBM job, if your instrumentation monitoring is very well and your interpretation design part is very well, you can find a volume loss of 0.2%, 0.3%. But in exceptional cases where the phase pressure cannot be controlled, or where the ground is very soft and where there is a chances of the collapse of the ground, sometimes it happens that several structures also get collapsed when the TBM is moving, that is the lying above the ground. So at that point, whenever we are measuring the volume loss, we can find that the volume loss has gone up to 1.25%, 1.5%. In Ahmedabad Metro, in the phase one, whenever I worked for Afghans, where Afghans was our designer, I was in the detail design part. So from the launching shaft to the Kankadia part, the ground was extremely soft, and we had a alignment that is going downwards and also in a curved alignment. So it is a very difficult alignment to manage for the TBM, because TBM cannot manage the curve very smoothly. I will explain that how TBM manages the curves. So at that point, there are 4, 5 points where some of the buildings got partially collapsed, and we found that at that the point, the volume loss was approximately 1.35%, 1.5%. So you can automatically correlate whenever the volume loss has gone very high. So then your settlement will also be very high, the surface settlement, and it will correspondingly whatever the superstructure is lying, the structure will also get affected. Okay. The next part, next slide. Okay. Okay, just leave this slide. Next slide, please. Okay. Now we come to the rock TBM. So the rock TBM, as I told you earlier, there are three types of TBM. One is open type of TBM, one is single shield, one is double shield TBM. Open type of TBM we mostly use in a very hard rock condition wherever we are not having any chances of collapse. We do not have any phase pressure issues, and we can do a very high advance rate. Even you don't need any type of support. So this is a very rare case of because it is very rare that you get a very competent, very hard rock condition because rocks mostly we found it is very highly jointed. There are lots of fault fractures. So open type of TBM is very idealistic condition. So mostly we are using single shield and double shield TBM. So single shield TBM, as I told you earlier, it's a very poor condition. It's a not very competent rock, and where you cannot take the thrust from the rock side rocks. That is, we are using in the double shield TBM. We are using the gripper pads to take the thrust from the rock. So in single shield TBM, we are using you are taking the thrust from the segments. So single shield TBM is mostly same as whatever the soil TBM you are seeing, but here the single shield TBM, the cutter head is more advanced. It is more competent to cut the rock, and but whenever it is advancing, then then the segment building is not taking place. So two operations cannot be simultaneously done in a single shield TBM. So the single shield TBM has a very slow advance rate, and if you take a operation cycle, it's very higher compared to a double shield TBM. Double shield TBM is used only where the rock is competent or whatever the gripper thrust the rock can manage, because the gripper thrust sometimes it can go up to 4 megapascal, 5 megapascal. So this amount of gripper thrust, whenever it is put on the rock, so the rock has the high bearing stress, so it can manage this thrust. So in the double shield TBM, we can use both the TBM movement and the segment building in a single operation. So double shield TBM is more advanced operation. You can have a very high advance rate. Your cycle time will be very low. Double shield TBM we have used in Kishanganga project for the headrest tunnel. We have used a double shield TBM. Okay. Now next slide, please. Okay. So this is the TBM layout. You can see. See, whatever the machine, it can be slurry machine, it can be earth pressure balance machine, it can be single shield, double shield, whatever it is. So you can see this machine. Whenever it is the full part has been built, it is approximately 150, 180 meter. It is, but the TBM part is only 18 to 20 meter, where we have the shield part of the TBM, we have the screw conveyor part of the TBM, we have the cutter head part of the TBM. So this part comes in several parts. So first, one all the parts is coming. So what we are doing, we are lowering these segments one by one. So first the cutter head is being lowered, then we are lowering the screw conveyor, and then there is a uh, cradle where you are putting the TBM parts, and then the TBM is being dismantled. And it depends on what is the length of your launching shaft, what type of TBM you have. That it is not necessary that you have to build all the TBM part in a once go. Because in Calcutta Metro we have a head and cut machine where you have to make the whole TBM part to facilitate the TBM operation. So it was approximately 180-meter long. So our launching shaft was approximately 200-meter long. In Delhi Metro, several projects they are using terratic TBMs where they are not building the full part of the TBM. They are lowering some part of the TBM and then they are starting the TBM, and then the rest part is being lowered gradually. So it depends on what is your launching shaft length, whatever, and what type of TBM it is. So you can you can assemble the TBM in that way. Now the next part. Next slide, please. Okay, now we come to the TBM main precast segment design principles. Okay, the next slide. Now, what is the key components of the segmental lining? So whenever you are talking of the segmental lining, so we are seeing a complete ring. So people, if you go inside the tunnel, you can see there are continuous rings, and every ring has a length of 1.2 meter, 1.4 meter, 1.5 meter. But whenever you see the rings has different parts. So if it is normally in metros, we are using a 5+1 part. So 5 is the segment part, 1 is the key ring part. So ring means that is the complete ring or complete part of all the segments. Now, how these segments are connected? These segments are connected by bolts. So the bolts can be longitudinal bolts, the bolt can be transverse bolt. So one bolt is the radial bolt, one bolt is the longitudinal bolt. So one bolt along the circumference, one bolt along the length of the tunnel. Now, so you can see there is a key segment and there are other parts of the segment. So the key segment is the joining part of the segment. So basically, this is one type of arch building concept. You are connecting all the part of the arches by a key. So here we are connecting all the segments by a key part. So the key part is the most smaller part of the segment. Other parts have different dimensions. So mostly, if you take the metro projects, every segment's average, the segment has a length of 6 meters, sometimes 5.5, 6.5 meters is the curved length. The key part is smaller. It is approximately 2.5 meter to 3 meters the length. Now you can see the all the curved segment parts, they have in a curved length. They have a tapered length. They are not a straight part. So why you are keeping the segments as a tapered? Mostly because of our tunnels are in a curved alignment. They are not in a straight alignment. So whenever the segments are in a tapered part, they can easily negotiate the curve. Because if I keep all the segments in a straight segments as a straight or a rectangular, then it cannot negotiate the curve because our alignment sometimes is becoming straight, sometimes is becoming curved, sometimes is the left hand side curve, sometimes the right hand side curve. So we are using a universal segment. Previously, what we are using that our taper was sometimes on the left side, sometimes on the right side. Now we are using taper on both sides. So taper on the both sides means it's a universal segment. So whatever the curve orientation, the segment or the TBM can automatically negotiate the curve. Now the if you see the ring length is mostly 1.2 meter to 1.5 meter. It depends on the diameter of the of the tunnel or the diameter of the TBM. The segment length, ring length is being varying. So normally in metros we are using 1.2 meter because our all metro projects have a finished diameter of 5.5 meters. Next slide, please. So if you look at the segment, you can find there are several grooves or several holes in the segment. So what is the part of this groove? There is one groove called bolt longitudinal bolt or connector. Mostly these grooves are used to put the bolts. There is one called bolt pocket. Another one is called the erector cone. Erector cone you can find at the middle of the segment. This is mostly the part through which the segments are being erected. Erected means the segments are casted in a mold. Then from the molds it is demolded. So that's the part where we'll put the our through which the segment will be erected, because the segment cannot be erected from any part, because if there is a eccentricity or if there is an unbalanced force in the segment, that will produce a additional force on the segment. So there is a defined part or there is a defined point through which the segment will be erected. So that is called the erector cone. Now, there are longitudinal joint, there are circumferential joint or longitudinal connector, circumferential connector through which the bolts will be put. Apart from that, there is an alignment dowel. Alignment dowel is mostly we put that the segments are aligned whenever it is negotiating in a curve. So alignment dowel mostly keeps the segments within a tolerance or within a defined alignment line. Apart from this, you can find there are small holes in the segment, very small. It can be approximately 10 mm dia, 15 mm dia holes, that is called dimples. Dimples are mostly that part from where we can interpret that there is no reinforcement, because after the segments is being cast, depending on the groundwater seepage or some additional requirements, sometimes we need to do grouting through these segments. Now, as the segments are reinforced segments, dimples are the points which can define that there is no reinforcement at that point. That is the point to which. So this is one typical part of the segments. If you look at the other segments also, they have this type of arrangements also. Now, the next slide, please. Okay. Now, as I told you earlier, that how the segments are getting connected. The segments are getting connected through bolts. So there are two type of bolts. One bolt is called the longitudinal bolt, one bolt is called the circumferential bolt. So you can find there is a longitudinal joint in the segment, there is a circumferential joint in the segment. So at the right hand edge, you can see there is a bolt that is connecting the two segments or two pieces of the segment that is being connected. So there is already a predefined groove in the segment through which this bolt is being connected. Now these bolts, there are different type of bolts. We are using straight bolts, we are using curved bolts, sometimes we call it banana bolts also. It depends on your type of the segment configuration, the bolts can be used. Now these bolts can be permanent bolts, these bolts can be temporary bolts. There are several scenarios after the segments are being installed and all the segments are in being placed. All the segments, after we do the wriggle survey, you find that all the segments are within the alignment and there is no movement inside the segment or the all the operation has been stabilized. It sometimes we are removing the bolt, but sometimes we are keeping the bolts also. So it depends on the contract in your contract or whatever the client has specified that whether you can remove the bolt or whether you can keep the bolts. But mostly at the cross passage location where you have to break the segments further to build the cross passages, at that location we are not removing the bolts because if I remove the bolts at that part, so whenever you're breaking the segment, so there will be a shearing between the two segments. So we are keeping the bolts mostly at the cross passage location. Apart from the bolts at the segment edge, you can find there is one place where you can see there is a plywood has been pasted. This is called the contact face where the segments will get mostly the segments will get the thrust. So this is the mostly the thrust face of the segment or where the thrust is being put by the TBM jacks. There is another thing called guide rod. Guide rod is an optional thing. It's not a mandatory. Guide rod we are sometimes putting on to control the alignment of the segments or to control the alignment of the rings or control the alignment of the TBM. Now in normal lining, normal cast in situ concrete lining, we are putting a waterproofing membrane. This waterproofing membrane can be a PVC membrane. It can be a spread membrane. But in precast segment, we are not putting a waterproofing membrane, rather we are putting a gasket because these segments are precast segments, so we cannot put a waterproofing membrane inside the tunnel. So what we are doing, we are putting a gasket. So gasket is a rubber, it's not a rubber, it's a polymer type of material and it's a highly compressive material. So whenever the two segments are coming in contact and when all the segments are being built, so automatically the segment gets compressed at the edge and the gasket is also getting compressed. And this gasket is forming a highly watertight joint. Now, this gasket, if it happens that sometimes the segments are not in aligned, or sometimes the segments get slipped between these two parts, or sometimes the offset is being built between the segments. That is called a stepping and leaping of the segments. So at that part, sometimes the gasket gets dislodged. So if it is a stepping and leaping part of the segment, you need to check that whether the gasket has been dislodged or not, and then you need to take appropriate measures to make the joints watertight. So these gaskets can be elastomeric gasket, this gasket can be hydrophilic gasket, this gasket can be combination gasket. So sometimes the client wants that they are in their project, they want a EPDM gasket, sometimes they want a combination of both EPDM and hydrophilic gasket. Sometimes they want the both gasket to be pasted and we make a composite gasket. So it's up to the client or up to the contract what type of gaskets do you want, and it depends on your groundwater scenario, what type of ground you have, what is the groundwater flow in through the ground, what is the hydrology of this area. So everything it dictates the type of the gasket you will need. The next slide, please. Next slide, please. Okay. Now, as I told you earlier, the ring tapering. The ring tapering is very important because this is the very important part how the rings will negotiate the curve. Because as I told you earlier, our talent alignment is never straight. Sometimes it goes straight, then it goes in a left-hand curve, then it goes a right-hand curve. Sometimes it goes upward, sometimes it goes downward. So in this case, we are using a universal ring. So what is the universal ring is doing? This is a, you can see it is a trapezoidal type of ring. So the both sides are tapered. So depending on the type of the curve, it can automatically negotiate the curve. So automatically, it whenever the left hand side curve is coming or the right hand side is curve is coming, So automatically the curve along the radius of the curve, the rings get aligned. But sometimes it happens that the ring cannot get aligned, and it sometimes the rings or the TBM gets out of the alignment. Then you have to check the alignment, and again you have to adjust your alignment. But mostly all our segments nowadays is a universal ring. Okay. Now the next slide, please. And next slide, please. Okay. Oh, no, just the previous slide one. Previous slide.
Yeah,
No, okay. The next slide. No problem. The next slide.
the thickness and length system.
Yeah. Now, how we decide the thickness of the segment, how we decide the length of the segment, how we decide the configuration of the segment. So, as I told you earlier, that there are lots of recommendations depending on the type of the diameter or the inner diameter of the tunnel. Now, if your tunnel diameter is 5.5 meter or up to 5.5 meter, so mostly we are using the inner tunnel diameter to the thickness within 18 to 25. So if you know the your inner diameter, so up to 5.5 meter, you can use more than 5.5 meter, you can use a ratio of the tunnel inner diameter to the thickness 18 to 25. So normally more than 5.5 meter, we are using a thickness of 300 mm, sometimes 325, sometimes 350 mm. In lower tunnel diameter, 4 to 5.5 meter, you're using a ratio of 15 to 25. And generally, a ring length is 1.5 meter is recommended for tunnel diameter 6 to 7 meter. If it is a very high tunnel diameter, then you are using a length of 2 meter. So normally, currently, you can see there are TBM dia of 11 meter TBM dia, sometimes 13 meter TBM dia. So tunnel, the segment lengths are more than 1.5 meter, sometimes up to 2 meter. Then another thing is that apart from the ring length, there's the main thing is the slenderness of the tunnel segment. Slenderness of the tunnel segment is the curve length of the segment and its thickness. Because we are not taking the straight length because all the segments pieces are curved. So we are taking mostly the curve length of the segment. And what is the thickness of the segment? So we maintain a ratio of 8 to 13. Normally 8 to 13 or normally up to 10, it is adopted. So accordingly, your curve length and your segment thickness will be adjusted accordingly. And as I told you earlier, the segment configuration depends on the tunnel dia. So if it is a very small tunnel dia of 4 meter, we are using a 5+1 configuration. So 5 is the main rings and 1 is the key ring. So for a higher tunnel dia, we are going up to 8+1, sometimes 6+2, sometimes 7+1. And if it is tunnel dia is more than 14 meter, we are using a 9+1 configuration. So it will be 9 segment pieces with one your key segment. Now there is a very common question being asked by the people that if I using a 5+1 configuration and if I use a 9+1 configuration, whether the segment thickness will be the same because the 5+1 configuration, whatever the ring dia I am maintaining, and whenever using a 9+1 configuration, how I maintain the same segment thickness. So that is why currently in the practice, I will explain you later that for the big tunnel dia, we are not changing the segment thickness. We are keeping the same thickness, but you are only changing the ring configuration. So there are certain assumptions we are using for a big tunnel dia compared to a small tunnel dia, where the segment thickness is kept universal. Because if I cannot use a segment thickness of a very high segment thickness, because the segment are being casted in molds, and molds are have a very common type of molds. So if I specify very higher segment thickness, so the mold cannot be available. Okay, the next slide, please.
Yes.
Okay, another thing is the segment thickness. Normally in the metro projects, we are using 275 mm, 300 mm, 325 mm. This is apart from the structural loads, whatever you're considering for the segment, there is another thing is your TBM shoe dimension. The TBM shoe, whatever the dimension it is. So if your segment thickness is not sufficient, so when the TBM shoe is being put on your segment edge where the thrust is being put, So there will be some eccentric loads being created. So your segment should be sufficient thickness so it can accommodate the TBM thrust also. So normally nowadays you can see for the higher tunnel dia we are using a segment thickness of 550 600 mm because our TBM shoe configuration for a higher tunnel dia is very higher. So we are keeping sufficient offset after the segment the TBM shoe is being put on the segment. So there is a sufficient offset between the two parts. So there is no eccentricity created. Now, as I told you earlier, the segment gaskets for waterproofing, this is a basically polymer material. It's called a ethylene propylene diene monomer. So it's a basically polymer type of material. It's a very highly compressible material, and this material has a design life of 50 to 100 years. So up to 50 to 100 years, this material will maintain its strength, will maintain its durability and its service life also. This material has a different manufacturer. They have different type of specification, and there are lots of tests. There are lots of things that you need to check whenever the material is being accepted. So as I told you earlier, there are different type of profile of this material. It's a standard EPDM profile. It can be composite profile. It can be with a hydrophilic profile also. But whenever those two segments are being coming in contact, and when all the rings are being placed, these gaskets get automatically compressed, and it creates a high watertight joint. So we are not putting any additional waterproofing material in the TBM segment. This gasket is the part of the waterproofing part. Now, the next slide, please. So this is the segment general arrangement. So you can see after the segments are being completely built. So one complete circle has been made. So you can see the different parts of the segment and they are connected by bolts. So you can see the radial circumferential bolts between the two segments. So, and apart from the circumferential bolt, there are also small dots, that is the longitudinal bolts. So both the circumferential as well as the longitudinal bolts, they are connecting the segments and they are making the complete ring. So each segment, it has different dimension, and accordingly the taper is also being decided. So this is the segment general arrangement. That is the first part of your segment drawing. So whenever you are producing any segment design or any segment drawing, your first is the GAD. So once the GAD is being accepted by the client and it is in line with all the tunnel dimensions, taking into account all the services, then we go for the reinforcement arrangement or the structural design of the segment. Okay. The next slide, please. So this is the segment general arrangement. You can see along the length. So when the rings are being built and when the TBM is advancing, so when the tunnel is being constructed, so you can see how the segments one by one they are being connected. Now you can see the key position is constantly changing. So the key position will be changing according to the TBM movement. This key position is not being fixed by the designer, rather it is fixed by the TBM operator or the TBM crew. They try to keep the TBM key position mostly within the 6 o'clock or 9 o'clock or within the 12 o'clock, but not in the invert part. They try to avoid keep the key in the invert part. They mostly try to keep the key within above the spring line part or mostly below the spring line, but not in the invert part. Now another thing you can see that all the segments, they are offset to each other. They are not in a single line. So there is always a offset between the parts of the segments that is being built. So this is the part that is helping the TBM to negotiate the curve. If all the segments are coming in a common line, then it cannot negotiate the curve. And if the segments are coming in a common line, then it is making a phenomenon called stepping and leaping. Stepping and leaping means that both segments are coming in a line that is leaping. And if the two parts of the segments are creating in an offset, in a plane, then it is called a stepping. So stepping and leaping should be avoided, but it cannot be avoided if it is a 3 kilometer tunnel, if it is a 3.5 kilometer tunnel. It happens that sometimes 5%, sometimes 10% of the length we are getting a stepping and leaping part. So if the stepping and leaping part, after checking it is still out of the tolerance, then you have to do some methodology to make the joints watertight. And at the bottom, you can see there are small holes in each part of the segment that is called the dimples that I already mentioned, that this is the non-structural part of the segment that is being used for additional drilling or additional grouting, whatever we need to do. Okay, the next slide, please. Okay, so
Yes.
this is the segment mold drawings where the segments are being casted. The segment molds drawings are being procured from the third party, and the segment mold drawing is in line with the segment GAD, that is the general arrangement drawing. So mostly all the segment molds are different for different project. So if I have a 5+1 segment configuration, so I need to make 6 molds separately. So we make a lots of molds we procure, because in my project, I suppose if it is a 3 kilometer tunnel, I might need 20,000 or 40,000 rings. So accordingly, I need to procure the molds. So inside the molds, whatever the bolt configuration, whatever the groups, whatever the sockets, whatever the dowels, everything, there is a predefined arrangement inside the molds. So whenever you are casting the segments, automatically these groups are being formed inside the molds. Now, these molds are being procured by the third party. So before starting of the project, at least you need sufficient time to procure these molds, and there are certain arrangements also needs to be changed according to the requirement of the project. And there will be certain scenario where I have to make a new molds. So there should be sufficient time for this mold procurement. Okay, the next slide, please. So this is the reinforcement after it is being put inside the mold. So now you can see that there is the groups you can see for the bolt, both type of bolts, as well as the longitudinal bolt, as well as the circumferential bolt in the left hand side, you can see the groups are there. So these groups will form, or this mold, whatever the configuration, it will make the groups for the bolts to be put inside. And these reinforcement are being put inside the mold, and after that we are putting the concrete, and after the casting there is a steam curing done, and once the strength is being achieved for the demolding, then we are demolding the segments, and then the segments are being casted stacked in a segment factory. And when the segment reaches its desired strength of M50 grade or M60 grade, whatever the concrete strength you're using, then the segments are transported to the TBM launching shaft. The next slide, please. So this is the segment casting factory. So you can see in a factory there are lots of molds for the project. And in the right hand side, this is the demolding of the segment. Once the segment has achieved its minimum strength, then we are demolding the segment by vacuum pads. So by vacuum pads, we are removing the segment. And as I told you earlier, there are certain defined points through which the segment will be erected. So this is already defined that which points I need to put my pulley, but through which I can erect the segment. And after the segments is being demolded, then it is being casted, stacked in the factory. So where the segment will gradually gain the strength. And in the extreme right hand side of the bottom, this is the complete ring once the segments, all the pieces are being built. So this is the thing you are seeing inside the tunnel. So this is one by one. So each segment has a length of 1.5 meters, sometimes 2 meters, sometimes 1.8 meter, or sometimes it can be 1.2 meter. Okay, the next slide, please. Okay, now whatever I discussed here, it is up to the only the segment configuration, the TBM type. So this is the basic things first of all to know before we go to the design part. Now, when the segment is being designed, it's a structural design. The geotechnical part is only up to fixing the ground parameters only. There are no role of the geotechnical in the segment design. It's a 80 to 90% is the structural part of the design. Now here we are taking three stages we are taking for the design. First of all, stage is the production stage. Second stage is the construction stage, and third stage is the service stage. Production stage means where the segments are being produced. So what we are doing, first of all, as I told you earlier, we are putting the reinforcement in the mold, then we are putting the concrete, then the molding of the segments is being done. And once the minimum strength is achieved, then we are demolding the segments. Then the segments are being stored. And once the segments is cured, and once the waterproofing membrane, that is the gaskets, are being placed, and all the segments are being checked that there is no cracks developed in the segments, all the segments have the dimension, they are within the tolerance, then the segments are being transported to the TBM launching shaft where the segments are being lowered. And during the lowering of the segment, you have to handle the segment very properly, otherwise it should not create additional moments. Then comes the construction stage. The construction stage is that once the segments are being lowered, then the segments are carried by a wagon inside the TBM, and then the segments are being placed at the trailing edge of the TBM through the TBM robotic arm, and then the segments are being built one by one. So there is a building process of the segment that is being defined by the TBM manufacturer or the TBM crew. So they define that how the ring will be placed or what is the configuration of the ring. So they mark the rings, and then they decide where the key ring will become. So accordingly, the ring is being built. So once the ring is being built, then we are doing the uh, primary grouting through the segment, through the holes inside the segment. So in the initial side, I show you there are certain holes inside the segment that is called grout socket. So through the grout socket, we are doing the primary grouting of the TBM. Once the primary grouting is completed, and if I need further that there is still seepage through the joints of the segment, then we are doing secondary grouting. So this is the production stage and the construction stage. So once the segment is produced, then it is being installed. Then comes the service stage. So once the ring is being completely built, then the segment starts taking the loads. Now the loads are mostly the ground load, the groundwater pressure load, the surcharge load. There is a bursting load. Bursting load means that when the segments are being installed, and once the complete ring is being put, then when the TBM is trying to move, then it is putting some additional thrust on the segments. And at the edge of the segment, there is a chances of the bursting. So you need to check the bursting reinforcement in your segment. Additional distortion means that if the rings are not being put in a proper way or the rings are getting some additional tolerance, then it can create an additional distortion of the segment. Apart from this load, there are earthquake load, there are fire load, there are explosion load. There might be load from the adjacent tunnels also. There might be load when the TBA, when the rails are being placed. There might be load when the trains are moving. Might be the train get displaced from the track. It can create a collision load. There will be a temperature load. There will be a sinkage. There are lots of loads we consider in the service stages. So for all is these loads, there is a partial factor of safety. So this partial factor of safety taken from standard segment design codes. So there is a segment design code from the British Tunneling Association. There is a segment design code from the German Tunneling Association. There is a segment design code from the American Tunnel Association. Currently, also ISSE in the Indian standards, we have a segment design code. So the partial safety factors are mostly considering the uncertainty in the loads. So for different conditions, you have different partial factor of safety. So whenever you are doing a ultimate limit design, you need to consider all these partial factors of safety to produce your desired bending moment and axial forces. Okay. The next slide, please. Okay. So first of all, we come to the production stages. So as I told you earlier, after the segments are being produced and then they are demolded, they are stacked. Now they are stacking. There is a very arrangement that it should be stacked in a proper way. And during the stacking, you need to check that if the segments are not eccentric to each other. If there is a eccentricity, then it will produce a additional moments. So during the production stages, you need to check what are the bending moments being produced. And is these bending moments are temporary moments? These temporary moments you need to check against your concrete or over the steel, whatever you have given against that particular compressive or tensile strength. Okay, the next slide, please. Okay, so this is the different stages bending moment and axial forces. There are formulas in the TBM design manual you can find. So for the stripping, for the storage, for the transportation, for the handling, there are what are the maximum unfactored bending moments produced and whatever the dynamic factors we are taking, you need to take into account and you need to check that in the temporary condition or in the handling stages, the bending moments are minimum or the forces are minimum, so it does not cause any unforeseen condition in the segment. Because if during the transportation or during the handling my segment get cracked, then I cannot use that segment, so it need to be discarded. So the designer point of the view, or if you are in the TBM tunneling part also, you need to check these forces, that these forces are within the allowable limits. Okay, the next slide, please. Okay. Now we come to the tolerances in the segmental lining, because every structure has its own tolerance. If it is a building structure, if it is an underground structure, even it is an underground station box, even it is a pile, it's a tolerance. So for the ring tolerance, we have our ring has its own tolerance. So the maximum ovalization, there is a tolerance. If it is a stepping lipping, there is a tolerance. If it is a gap between the contact faces of the segments, there is a tolerance. In the vertical position of the segment, it is tolerance. So whenever your TBM rings has been completely built, and when the TBM has been removed from the tunnel, we are doing a regal survey. So in the regal survey, what we are doing, we are getting the as-built profile of the every rings. So if it is a 10,000 ring, we'll get the 10,000 ring as-built profile. And then we are comparing our design profile with the as-built profile, and we'll see that whether these both profiles are lying within the allowable tolerance limit. If it is not within the allowable tolerance limit, then you need to report to your designer. So the designer will suggest his recommendation, because once the ring is been built, it is cannot be removed. I cannot put an alternate replace ring, because it will cause a distress within the tunnel. So if it is out of tolerance, the designer will suggest that what to do the remedial measures, so the structure can achieve a 100-year design life. Okay, the next slide, please. Now we come to the construction stages. So construction stages, as I told you earlier, all the TBM, EPB machine or slurry machine, they are taking the thrust from the segment. So you can see here that the TBM thrust pad is being put on the segment, and it's a temporary thrust, but it's a very high thrust, because depending on the ground condition, different machine apply different type of thrust. So if it is a metro project, normally we are putting a thrust of 20,000 kilonewton to 25,000 kilonewton, sometimes 27,000 kilonewton. But if it is a hard rock machine, the thrust will be very high, 35,000 kilonewton to 40,000 kilonewton. So this amount of thrust is being applied on the segments. So your segment needs to bear this thrust, and there is a chances that due to this thrust at the edge of the segment, some tensile stresses can be produced, some very high bearing stresses can be produced. And if your segment is not of sufficient thickness and it is not compatible with the segment shoe, then the bearing stress, whatever it is produced, or the contact area will be reduced, then it will produce a high bearing stresses. So this amount of whatever the stresses this is produced, the segments, what you are doing, you are putting some additional reinforcement at the edge of the segments to counteract this thrust. So this is called a bursting stresses. The bursting reinforcement you are putting in additional. So in a segment, apart from the main reinforcement or the transverse reinforcement, we are putting a bursting reinforcement, we are putting a chair reinforced chair bursts also. So all this reinforcement take into account of this temporary forces. Now the next slide, please. So this is the configuration by which you can calculate what is the bursting thrust is being produced and what is the corresponding tensile stresses. So you can compare with your own material stresses. So this is the formula by which you can calculate the thrust. This is for the construction stages. This is not for the permanent stages. Okay. Now the next slide, please. And another thing is the tail skin backgrouting pressure, because after the segments is being installed, I told you earlier, there is a gap between the trailing edge of the TBM and the segment. So that gap we need to fill as soon as possible. Otherwise, this gap will create some additional movement of the ground inside the TBM, and also it will produce some additional surface settlement of the ground. So this is called, this needs to call the this is to be filled by grouting. So this grouting also creates some back grouting pressure, because whenever you are grouting, they'll sometimes the grout does not goes inside the ground, but it comes outside. And if it is going inside the ground, it is also producing some additional pressure inside the ground. So this is a temporary pressure, but we still need to account for this backgrouting pressure. And this grouting pressure, it depends because mostly we are giving a pressure of 1 bar to 1.5 bar. So it can be 100 kPa to 150 kPa. It is a radial thrust inside the segment, and we are applying a factor of 1.25 because, as I told you earlier, that every load needs to be applied as a partial factor of safety to consider the uncertainty. The next slide, please. Okay. So this is the grouting pressure, how it is acting. Mostly we are considering the grouting pressure at the crown of the TBM or crown of the tunnel. We are considering this grouting pressure. So this grouting pressure can be a primary grouting pressure. It can be a combination of primary grouting as well as secondary grouting. It depends on your ground permeability, whatever, how much gap is there and how consistent is your grout. So the grout can flow inside and it can apply a pressure. This is also a part of a temporary loads on the segment, and it is part of the construction stages only. Now the next slide, please. Now we come to the final stages. So all the loads that we have discussed, the grouting load, the bursting reinforcement, the handling, this is all the temporary. Up to this, the TBM has been, segments has been installed. Now, from the final stages, we are assuming that all the rings has been placed. My full ring has been developed. My all the segments has been grouted. Everything is perfect, and now the segment can take the loads. So from this point, the segments of the ring starts taking all the loads. So it can take the ground load, it can take the groundwater load, it can take the surcharge load, earthquake load, fire load, explosion load, all the loads that I discussed you earlier. Now these loads can be configured in a beam string model or in a FEM model, whatever is suitable to you, you can do this analysis. By this analysis, you can determine the axial forces and bending moment that is coming at the different parts of the segment. And by your moment interaction diagram, you can check whether your grade of the concrete, your grade of the steel, the cover in the reinforcement, the number of reinforcement you have put, the thickness of the segment, everything is perfect or not, you can check in these stages. Now, the next slide, please. So there is another stages called the joint busting load. The joint busting load is mostly what happens that in the, if you look at the segment configuration, there is a small groove at every segment that where you are mostly putting the our waterproofing membrane. So if you consider the contact area, here we have a reduced contact area when the segments are being joined to each other. So this part is having a reduced contact area, and that is producing some joint busting load here. So this joint busting load you can also estimate and you can check against your allowable stresses. So here you have to take care of your additional reinforcement because as the area is reduced and the whatever the forces are produced here, so here there might be chances of the high stresses zone. So here you need to put some additional reinforcement to consider the joint busting load. Okay, the next slide, please. Okay. Another thing is the additional distortion. Additional distortion means that if the segments, whenever they are being built, if the two parts of the segments are not in a proper line or they are not contacted properly or there is a gap, that can produce additional distortion. And sometimes it is called as a bird's mouthing. Bird's mouthing means that the two segments are not joined and they are offset to each other and they produce a gap just like a bird's mouth. Or so there is, if this type of things are being produced, then it can produce some additional distortion and some additional forces. So before the segments are being lowered in the shaft and they are being built, so you need to check all the segments in a universal ring. You need to check that whether all the segments are being in proper contact. So if they are not in proper contact, then you have to replace the segment. So these checks are basically done before we putting the segments inside the launching shaft. So this is the checks before we are putting the segments inside the TBM. So this is one of the very strict phenomenon that is checked by the client. That is the bird's mouthing before the segments are being lowered inside the TBM. Okay, next slide, please. Now now we come to the fire loads. These fire loads are now becoming very popular in the tunnels because there are lots of accidents where we find that due to the fire load, the segments, the concrete is getting affected, the strength of the concrete is getting reduced. Sometimes there are spalling of the concrete, sometimes there are reduction in the thickness of the concrete, and there are certain European codes also that specifies that your segment needs to be fireproof. There should be a certain fire resistance, or there should be certain mechanism inside your segment design that can handle the fire load. So what is the fire load? There are lots of fire curves. There are you can in any type of standard tunnel design manual you can find there are standard fire curves being produced, but mostly we are using the zonal method in our design, and we are what we are doing we are determining that what will be the maximum temperature that will come inside my tunnel. So that depends on what type of vehicles that is moving inside your tunnel. So in road tunnels, we are specifying the wattage of the fire. So some road tunnel we are specifying 30-watt fire, some road tunnel we are specifying 50-watt fire. Some the strategic tunnels we are currently going up to 100 megawatt fire. So currently this Chinani Nasri tunnel, it has a, I think it is a 30 to 50 megawatt fire it can handle. So depending on the fire load, so what is the maximum temperature, what is the inclination of the temperature, what will be the duration of the fire, that needs to be decided. On the next slide, please. Okay. Now, whatever the fire curve you're using, then you need to decide that first of all you need to decide the fire curve. So if it is a 4-hour fire curve, it is a 2-hour fire curve you are using. So mostly in the metro projects you are using a 2-hour fire curve. If it is a road tunnels you are using a 4-hour fire curve. So what is your temperature? So depending on that you can determine what will be your exposure to the fire. Okay, the next slide please. Now there is a standard curve from which you can determine that depending on the type of the temperature that is generated during the fire, what will be the thickness of the concrete lining that will get exposed. So here you can see that what is the distance up to the how much distance my lining gets exposed. So from here particular temperature and what is the thickness of the lining. So if it is a 275 mm thickness of the lining, so might be 30 or 35 mm thickness might get exposed to the fire. So that thickness will not be effective in your structural part. So your net thickness of the lining will be 240 or 245 mm. But since the loads are same, so we need to check that even after the reduced thickness, my segment is still capable of handling all the service loads. So this is the fire curve, fire part of the design that after the reduced segment thickness, whether still the segment is capable or the ring is capable to take all the loads that we need to check. So this is an additional check apart from all the loads that during the fire, this reduction of the segment is still capable of taking all the service loads. And and current days we are using PP fibers in the concrete lining. This PP fiber has a very high melting point, and this PP fiber will try to prevent the concrete get exposed to the fire directly rather than it is itself is getting exposed, and due to the high melting point it can absorb the heat of the fires also. So apart from the main reinforcement, we are using also PP fiber as a 2 kg per cubic meter of the concrete, sometimes 1.5 kg per cubic meter of the concrete inside the segment to make it as a fireproof for the future fire loads. Okay. Now the next slide, please. Okay. Then we come to the seismic loading part. In the seismic loading part, previously we are using seismic coefficient. So we're using vertical seismic coefficient, we are using horizontal seismic coefficient. And then these seismic coefficients, we are determining the seismic forces by FEM, or you can use your empirical formulas, and then you are adding to your static forces by partial factor of safety. Current days, we are using ITA guideline, and the ITA guideline, they have called a guideline that is seismic design and analysis of underground structure. This is called the HASHAS guideline. So the HASHAS guideline, what he has considered the axial and the curvature deformation And there is a two phenomenon that is called ovaling and racking. Ovaling means if it is a circular segment, partially it gets ovalized due to the nature of the ground, due to the confinement of the ground and whatever your seismic wave propagation. Racking is mostly applied to the cut and cover box structures. So due to the raking, ovaling, or due to the curvature or axial deformation, you can determine whatever your seismic forces. So this is more realistic, that is in line with the actual uh, effect of the seismic. So if you consider only the seismic forces as a seismic coefficient, that is not a realistic seismic analysis. So nowadays in metro projects, it is very mandatory that you need to follow the ITA guideline to determine the seismic forces, and you need to simulate your actual seismic movement or whatever the effect of the segments that can happen, that you need to simulate here. Now there are two types of earthquake condition we are considering. One is called the maximum design earthquake. Another is called the operating design earthquake. Maximum design earthquake is the experiment, is the extreme loads that it can happen in a very rare thing. That is, if you are considering it can happen 1 in 1,000 years, it can happen in 1 in 2,500 years, it can happen. But that is the maximum design earthquake force we are considering. Operating design earthquake force that has a probability of occurrence of 40 to 50%. That is normally the earthquake it comes. It can come once in a year, it come once in a 2 year, once in a 5 year. It's the operating design earthquake. But all type of underground structures we are designing both for the maximum design earthquake as well as operating design earthquake. So whenever you are designing a segment apart from the static loads, you need to check the segments for both earthquake condition as well as operating as well as maximum design earthquake. So in the operating design earthquake, you are applying a factor of safety of 1.2. In a MDE case, we are applying a factor of safety of 1. But the horizontal and vertical seismic coefficient as well as the seismic spectrum is different in the MD and OD. Okay. Now the next slide, please. Okay. Now we come, whatever this is things we have done is mostly the ULS design or the ultimate limit state design we have considered. Now we consider the serviceability limit state, where you are considering mostly the cracking, the deformation, or if any type of additional stresses are produced, that is the serviceability limit state of the segment. So the cracking, there are defined crack width for the segments. It is 0.2 mm to 0.3 mm we specify. So if this criteria is being exceeded, then we need to do our own structural checks to check whether the segment is still safe in the cracked condition. As I told you earlier, for the deformation, there can be certain deformation at the joint, at the offset, or there can be deformation of the ring also due to the ovalization of the ring, due to the service loads of the ring. So mostly in the serviceability limit state, we are checking the deformation of the rings and we are checking the cracking of the individual rings. The next slide, please. So this is the criteria for the crack width, as I told you earlier. So there are different conditions of the crack. It can be a very dry crack, it can be a moist crack, it can be a wet crack. So depending on your type of the cracks, so the crack width has been specified. So accordingly, you need to check that what is your groundwater, what is your seepage condition, and what is your crack width. So if it is not fitting with this crack width, so you need to check with your structural engineer that whether for this particular crack width or whether the crack segments, my my segment is still satisfying the serviceability limit criteria, or it is still safe within the service loads or not. Okay, the next slide, please. Now we come to the durability. Durability is the last part. That is, whenever you are designing a concrete lining or whether you're designing a precast segment, you are specifying a 100-year design life. So 100-year design life means that does not mean that 100-year, whatever the loads it will come, the segment will handle all the loads. 100-year design life means that the segment is durable against their certain conditions. So first of all, condition is that the reinforcement will not get corroded by the chloride attack. It will not get corroded by the carbonation attack. It will not get corroded by the sulfate attack. It will not get corroded by the acid alkali reaction or acid attack or any type of frost attack or any type of freezing fine condition or any type of spray current protection. So all these conditions in the service stage the reinforcement or concrete will not get corroded. So reinforcement will not get corroded or the concrete thickness will not get reduced. So this is the durability part. So in the durability part, what we are doing, next slide please. What we are doing, we are there are British guidelines, or you can take any type of ACI codes also. They specify different parameters or different exposure conditions for different environment, and there is a certain limit for the different chemicals. So for the carbonation, for the acid, for the sulfate, for the um, uh, alkali. So what type of exposure for different exposure condition and whatever the allowable limits they have specified. So whenever you are doing a geotechnical investigation, you are getting some soil sampling results, some water sampling results. So from the soil sampling and the water sampling results, you need to see that what is the current atmospheric condition or current nature you are handling, or what is the current ground corrosion scenario where you are making you are installing the segments. So from there you can get an idea of what is the current exposure condition of my concrete or steel at this particular project. Okay, the next slide please. So here you can see there is a different type of ground cover has been specified. So for different structural class, that the structural class comes for the exposure condition as specified by the American Concrete Institute. So we are specifying the reinforced ground, we are specifying the cover over the reinforcement. In IS code, you can see that they have specified a cover of 40 or 50 mm minimum over the reinforcement. And if I consider a durability part, the minimum thickness of the segment is 240 mm for a short column, because we are considering this segment as a short column structure. So as per IS code, for a 40 mm cover, our minimum thickness of the structure should be 240 mm. So we are using in a metro project, we are using as a 275 mm. So we are satisfying the IS code criteria, but also we are checking from the durability criteria for the different exposure class. Okay, the next slide, please. So here you can see that for the different exposure class, so there is a minimum strength it has been specified, and also we are specifying the what is the limits of concentration in the material. So here what we are doing, we are specifying the exposure class, we are specifying the tolerance limits of the chemicals, and accordingly we are specifying the cover over the reinforcement, and then you have to adjust your mix design. Okay, the next slide, please. Okay, the previous slide, please. Previous. The previous slide, please. Yeah. So what we are doing, so from the exposure class, we are determining what is the minimum strength needs to be achieved for the concrete, and what will be the limits of the concentration of the materials. And accordingly, what you are doing, you are adjusting in your mix design. So there is a separate table I will provide you later, where we are specifying the cement content and type of the cement depending on the exposure class. So in the mix design, you need to check that the cement contents or whatever the additives you are providing, that is within as per the standard guidelines. So in one of the project, what we did for the durability, we checked the mix design as proposed by AFCONS for the segments, and then we have taken all the mix design parameters in a software called Live 365. So where we can see that what is the current design life of our design. So if I specify, we have specified a design life of 100 years, but for the particular mix design, against the exposure class or against the chemicals that has been associated with this ground, we found that our design life was going approximately up to 250 years. So our design life for the particular segment design, it is more than the allowable limit. So this way you can check the durability. So durability is always associated with the your ground or the water or the current atmospheric exposure of the segment. It doesn't has to do with the structural loads. Okay. Okay. The last slide, please. So here, this is the standard codes for the segment design. We are using American Concrete Institute codes. We are using the British guidelines. We are using the German Tunneling Association guidelines. We are using the Singapore Transport Association guidelines. Currently, also we have a IS code for the TBM and the segment design also. So different projects or different people have their different inclination toward applying but all the guidelines are almost the same. But in the current industry, American Concrete Institute, there is a guideline called ACI 544. That is the latest, just specifies the design both for the conventional reinforcement segment as well as the fiber reinforcement segment. And nowadays also, apart from the conventional reinforcement, you are using fiber reinforcement segment also. So fiber reinforcement means it's a steel fiber, and we are making a hybrid type of segment. We are not using only fiber; we are mixing both segments, both reinforcement, conventional reinforcement, and fiber as the reinforcement part in the segment. So nowadays we are not only using steel reinforcement. Apart from, we are using a rather mix of fiber and conventional steel reinforcement as a hybrid reinforcement also. And the polypropylene fiber is mostly used for the fire load, to take into account of the fire load of the segment. Okay. So this is the overall precast segment design concept. It's a very lengthy, it's a very huge topic because it cannot be completed within a short period. But as much as I have covered this part.
Yeah, sir, excellent presentation. And yesterday I saw this, so I was overwhelmed to present it. And I would request participants to ask your questions in the chat box. I think few of the questions are already coming. So we can take the questions for next 10 to 15 minutes or so.
Yeah.
So, yeah, there are some questions which have come. I will start one by one. Yes. Someone is asking, sir, PPT after the lecture. Yes, you will get the presentation copy. Then excellent presentation. How bolts are protected from corrosion? Uh,
The
Niranjan,
bolts
will
are
you?
protected from corrosion. We are putting a plastic sheath around the bolt. There is a plastic sheath. Whenever you are putting the reinforcement in the mold, then we are putting a plastic sheet in the mold on the bolt groups. So automatically we are making this bolt corrosion. But these bolts, as I told you earlier, some bolts are permanent, some bolts are temporary. So some projects we remove the bolts, some projects we keep the bolts. It's up to the client because it depends on that. Once your ring is completely built, and if you check the as per the survey that the rings are in aligned, then you can remove the bolts because it's a continuous ring. So automatically it get connected with each other. So some bolts are temporary during the ring building or to keep the rings in a aligned position. And after certain point, you see that the rings are in a perfect position. There is no such deviation or the tolerance are within allowable. Even all all the loads after application of the loads, because here what happens, it's a ring part, so almost it's a hoop thrust part. So you don't get very huge forces. It's a very low amount of bending moment and axial force you get in this segment. So the bolt is not as a structural port, bolt is only to the hold the segments or keep the segments in a line only.
Okay. So, sir Niranjan, sir, I think your question is answered. Mr. Sujit is asking one question: how to evaluate real volume loss? Is there any instrumentation or SCADA arrangement while TBM is in operational?
Uh, Nowadays, TBM, this volume loss is very vague concept because it's very difficult. Because in my project in 2018-20, what we used to do, we used to measure the skip volume. So whatever the mark is being extracted from there, we used to measure the skip volume, and then we approximately used to determine what is the volume loss. But there is a very interesting thing we did, that whatever the surface settlement profile you are getting when the TBM is moving ahead of the TBM or behind the TBM, from the surface settlement graph, you can back calculate the volume loss. Because suppose you have a volume loss of 0.5 to 0.75%. Now your instrumentation monitoring arrays are put at every 25-50 meters. So if you make some real-time arrangement, it will automatically calculate that how the surface settlement profile along the head of the TBM or behind the TBM is going on. And from there, from the maximum settlement, whatever is or average settlement, you can back calculate the volume loss. But
Okay.
there is no direct methodology to determine the volume loss. It's a sometimes some sort of back calculation we are always making. But nowadays the TBM is being advanced, so it is automatically calculating whatever the volume is being extracted, how much mark we are removing from the excavation chamber. So it's almost real time is being done inside the TBM. But the instrumentation part you can do through your real time. But in as in our surface settlement, we are using only BRT, small surface settlement markers. So we do not read real time unless you have some inclinometer, then you can do it. But here we don't do real time TBM.
Okay, great. Yeah, there's a next another question by Niranjan sir. He's asking, do you have any in situ water tightness test?
In situ water tightness test we don't do. What we are doing, we are as I told you earlier, the gaskets, they have certain amount of testing done. So the gaskets, whenever it is being procured, so there is a material testing certificate comes with the gasket, and there is a standard curve that for particular load, what is the closure of the gasket. So suppose if you applied 1,000 kilonewton load and your gasket closure is zero point 0.2, 0.7, suppose I say. So you need to check that load deflection curve of your gasket. That is the give you the water tightness. Otherwise, we are not doing any extra water tightness test of the gasket.
Okay.
Because the gasket comes with the manufacturer. So the manufacturer ensures that whatever the specification or the that is being that is in your part of the project, that is being met by the his product.
Okay. Yeah. Participants can see the your hold on the subject, like so many minute things, and it's really difficult to cover the topic in 1 hour, which you have done very nicely.
Thank you,
Mr.
sir.
Sushil Gupta has asked one question. Kindly share how to track the segments during dispatch. Any digital solution?
Not a digital solution. It is a before transporting the segment that I told you earlier that the your segment should not have any cracks. So what we do, we are doing some laser technology to see that is any embedded cracks in the segment. Because what happens if there is a embedded crack inside the segment during the stacking, and whenever you are installing that segment, that crack might get more wider when the segment is getting the thrust from the TBM. So whenever before the transporting the segments, we are checking the each segment by some in situ testing or by some laser technology that there is no embedded or there is no fine hair cracks in the segment. Because if the segment is getting cracked once the segment is installed, then you cannot replace that segment because already it is in a stable position. Now, if you try to remove that segment, then it will become make a unstable one. And this happens in lots of projects I have seen that in naked eye you cannot see the segment crack, but once you try to install the segment, when the segment is getting the thrust from the TBM, then the crack starts opening gradually. But as I told you earlier, the cracks has a tolerance limit. So if it is within the tolerance limit, the crack is not detrimental to your structural life. And what type of crack it is? If it is a very dry crack, if it is a wet crack, it is a moist crack. So in Lucknow Metro project, we got several cracks in our in our first drive. We got several cracks. So later we clarified these cracks are not due to structural. It's mostly due to the misalignment of the thrust of the TBM or some sort of cracks that has been produced during the casting, during the stacking. So these are not a structural cracks. So thus the cracks does not accounts that there is insufficient reinforcement in the segment. So if you are getting crack, that does not mean that it is a structural crack. You need to see the crack. You need to analyze the what is the origin of the crack, and what is the further effects of the crack.
Yeah, great. Engineer Azam is asking, sir, what is a minimum and maximum percentage of
Yes,
reinforcement provided and how to calculate it?
the minimum reinforcement, it is all because, as I told you earlier, the segments are almost designed as a short column. So we are always trying to put at 0.8% to 1% within the segment, because it happens that, as I told you earlier, if it is a very hard ground, or if it is a very hard rock, or if it is a very stiff soil, you might get very less loads. So if you practically calculate, your segment does not need reinforcement, but still we are putting some reinforcement to avoid the cracks in the segment, because in terms of serviceability limit, we are putting a minimum reinforcement. Though the maximum reinforcement, because we are trying to put within a limit of approximately around 1.5 to 2%, because the more the reinforcement you put, is very difficult to compact the concrete. So the segment should be placed in such a way that there should be gaps when the vibrator is going after pouring of the concrete. Because if this is not the same as a diaphragm wall. Diaphragm wall has a very high axial load, high bending moment, because diaphragm wall is taking the whole thrust of the ground, whole thrust of the water. But in the segment, it is already a circular configuration. So due to the hoof stress, the loads are getting automatically dissipated along the perimeter of the lining. So if you see, unless it's a very soft ground, you have a very low bending moment. Sometimes you get a very high axial force. So if you compare in the MN curve, only 10%, 15% of the MN curve is being utilized in a segment design, if it is in a very high uh, strength ground. But still you are putting reinforcement to avoid the cracks or to take into account of the serviceability condition.
Yeah, just a question, sir. In the same line,
Mm.
is anywhere have we used any GFRP reinforcement, or are we using
Yes, yes,
only?
yes. Yes. GFRP reinforcement, you can use that is same thing I told you, that you can use fibers also. Nowadays you are using steel fibers also. GFRP you can use, but in practice it is a hybrid type. We are not using a purely GFRP. We are using a mixture of conventional and GFRP reinforcement, because at the edge of the segment, where the segment will get the thrust from the TBM shoe, we are putting the reinforcement so the splitting strength can be accounted. Because if you use a fiber, so fiber may not account for these bursting stresses.
Okay, yeah. Yeah, there's a next question coming from Vijay Zoreji. He's asking how do wriggle survey and how the offset of rigs can be post construction corrected.
It cannot be corrected. It is, as I told you earlier, once the TBM has been extracted, once every backup, all the things has been extracted, we are doing a legal survey to check ring by ring that what is the shape of the ring and where it is exceeding the tolerances. So whatever part it is exceeding the tolerances, we are assuming that that part might be the joints between the segments has become, some offset has been produced, or might be the gaskets has been disturbed. So we are doing additional grouting at that part. So that is why the tolerances of the segmental lining over the diameter, over the radius, or over the maximum roll, it is being specified to see that whether if any segment between the joints has exceeded its tolerance. So that part we are doing some additional grouting or some additional strengthening to make it as a watertight, because you cannot replace that segment. It's not possible that my six segments, one segment has gone out of tolerance, I replace that segment and I build a new segment. It's not possible, because it's a continuous system. So once one part is getting affected, or once part you try to remove, the whole system gets affected. And we tried to do this in Lucknow Metro project near Husainganj station, and we found that the part where we are trying to removing the segments, along the 3-4 segments it is getting automatically affected, because it's a continuous part. No,
Yes,
it's a 3D as well as a 2D. So it is a
yes,
continuous infinite length of the segment.
correct. Yeah, there's a next question coming up from Engineer Manoj. He has two questions. He has given also a compliment, very insightful session. And the first, I'll take two questions one by one so that it is easy for you to answer separately. He's saying we frequently see segment cracking occurring during TBM maneuvering along sharp curves. What are the most effective mitigation strategies or countermeasures to minimize the localized stresses during ring building and show?
Yes, there is a articulation. There is a phenomenon called articulation. There is a two things called passive articulation and active articulation. So articulation mostly controls that how in a very steep curve the TBM shield and accordingly the lining will follow the curve. Nowadays, all the TBM machines are coming with the active articulation, but still we found that in a very steep curve, sometimes the TBM shield because it happens that when the tail end is being extracted by putting some additional thrust, it gets all the segments is getting damaged when the tail end is trying to move ahead. So it's not possible to always to move the TBM in a very smooth curve. But if you want, I can send you a separate article on articulation. Basically, the articulation phenomenon controls the steering of the TBM. So it's not like a vehicle that we are using a power steering and the vehicle can 180-degree carving can negotiate because TBM you can imagine it's a 200-meter length. So whole thing and accordingly it is carrying all the segments also. So the whole part, if it has to be negotiated in a very smooth way, and it cannot be that the whole part gets uh, can negotiate the curve in a one go. So we are using an articulation phenomenon. So articulation for the articulation, there are articulation jacks inside the TBM. So the articulation jacks basically control the steering of the TBM, and nowadays we are using active articulation. But still, if you are interested, you can send your email address to Vivek sir. I will send a separate article or separate explanation on this part so you can understand that how the TBM can steer in a very steep.
So basically, very vast subject. So
Yes,
I think probably we need to arrange few more sessions in
yes, yes.
say coming days. Yeah, Mr. Manoj has the second question. Have you ever experienced a situation where a precast segment had to be removed from the ring building while still inside the tail shield, specifically to inspect the tail skin grease brusher because there was a huge amount of grout leakage? If so, could you please explain?
This situation I have never experienced, but you can do during the TBM building. You can do it depending on whether your if there is a very comfortable type of ground solution, because if it is a very high water ingress, then your brush might get affected. So it depends on what type of ground scenario you are handling. Because in intermediate the TBM ring building, if you are finding that some rings is getting damaged, you can replace the rings. But it is a very risky scenario because in one of the project in Bowbajar that where ITD was doing, the water pressure was so high that the brush got dislodged from the TBM. So it depends on your type of the ground and what is your groundwater ingress at that scenario. But I have never experienced this type of scenario.
Great. Yeah, there are a lot of compliments coming. Excellent illustration, very insightful presentation. Thanks to ISSE for organizing the session and Debasis especially. He agreed the request at a very short time in spite of the busy schedule which is going. Yeah, thank you. Then there is another question coming up from Engineer Gautam. He's asking, major project face problem of horizontal stacking due to space constraint. Vertical stacking is a new practical solution. So, sir, what do you say?
Article stacking, I have never done. You told what you told is very correct thing that there is sometimes we have get very limited areas for the stacking, but I need to explore more because I never done this vertical stacking. I never heard or never seen any journals or any project or any of my colleagues because always you go for a horizontal stacking. But I will still explore this part. I will come back to you.
Great. Yeah, there is another question by Engineer Sushil Gupta ji. What should be the ratio of rebar plus fiber as per design? do we have any standard design and
Yes.
its credibility? Please share.
Yes, yes. There is a ITA guideline. They are currently, as I told you earlier, that Indian International Tunneling Association, they recently came with the fiber info segment. So there are lots of design guidelines. There are lots of checks you can do for the fibers reinforced segments. Even it is a you can do for a composite segment, you can do for a hybrid segment, you can do for a pure fiber segment. But I will prefer you follow the American Concrete Institute guidelines. That is the latest guideline for the fiber info segments. And if you take up the ratio, it depends on the fibers are very useful if the ground is very competent. Because suppose if you have a ground of a mixed ground type or in any type of the along the alignment, there might be a fault, there might be a loose zone, that part fibers are not very highly recommended because fibers are very good for uniform ground nature. Even I practical for my experience, I have never used fibers for precast segments, but in cast in situ lining in USBL project we have seen that fibers are very good in competent ground scenario. But wherever it is a low cover scenario where there is 100% of the ground loading comes on your tunnel, or wherever there is a thrust, or wherever there is a squeezing ground type of scenario, that part we seen that the lining is getting cracked because fibers cannot handle unequal loads. Or if it is a very mixed type of ground scenario, fibers are not very effective. Rather than you can rely more on the conventional reinforcement. So it depends on your ground type, your loading type. You can use a mix both fibers and both conventional reinforcement. In Neom project, I have seen that designer, they made a mixture of approximately you can take as a ratio of 60-40. So 60% was on the fiber, 40% was on the steel. So they mostly put on the steel where it is the critical part that the thrust phase or where we are getting some additional tensile load, they are putting the steel reinforcement. Because the fiber, what is happening, the reinforcement you are placing in a proper fashion, in a proper spacing, in a proper arrangement. But fibers, what you are doing, you are mixing in the concrete. So it comes as built within the concrete. So it might depend on your pumping system, it might depend on your mixing, how proportion you mix. The fiber not getting equally distributed on the reinforcement. Some part of the reinforcement can get a heavy concentration of fiber, some part of the reinforcement can get a very low concentration of fiber. So there is a still the people who are in the construction industry, they don't agree on the fiber strength or more on the fiber effectiveness.
Okay, great. Yeah, there are a lot of compliments coming. Excellent presentation. Vijay Zoreji sir is asking about tunneling instrumentation and monitoring. So if you are having some kind of document or a SOP on this thing, you can share, sir.
Definitely, I
Then
will share. Tunnel instrumentation monitoring. It's in bore tunnel. We are not doing any monitoring inside the tunnel. Only at the cross passage location, we are putting some BRT to check the if any compression of the segments. Otherwise, all the instrumentation monitoring is done above the ground. All the buildings, all the surface, ground surface, we are doing the instrumentation.
Yeah,
But if you
Ranganath
want, yeah,
Satamji, ISSE Secretary Ranganath Satamji has asked a question, sir. The lecture was highly insightful and practical point of view, assist the underground and on-site application of tunnel design and construction. Then Niranjan sir is asking about dimples after fixing of the lining. What about dimples after
no
fixing of
dimples.
lining?
No, dimples comes inbuilt in the mold. So as I told you earlier, the dimples are the part where we are not using any type of, we are not using any reinforcement. So if I need additional grouting or if I need to do additional drilling, so dimple is the only part where is the non-reinforcement zone. So the dimple comes inbuilt within the segment mold. So if you refer my presentation in the segment mold part, you can see already dimples are defined there. So it comes as built within the molds already.
Yeah, I'll take a last question because we are shooting 2 hours time
Yes, yes.
because the recording is happening of this session. Engineer Chandra Prakash is asking for UHPC concrete, you can use NFP 18710. So I think you can answer this question, sir. I
This
don't
I
know.
need to explore because I am not comfortable with this one. I will explore and I will come back to Vivek, sir. I will explore.
Yeah, that was a wonderful session, and thank you, sir. Thank you very much on behalf of ISSE for giving a very insightful session and patiently handling all the question and answers. The chat box is really flooded, but there is a time limit for every good thing. So now, if anyone is having any questions, so you can feel free and send the questions to me by today evening. I'll collate the questions and forward it to Debasis sir, and he can answer them at his ease. Maybe by next week, he'll give the responses to all the questions. I'll share it in our WhatsApp group. The YouTube recording of this session has happened, and I will be sharing them to you all very soon. And I'm happy to announce that with this session, we have completed 1 year of this activity. So I thank you all, ICC audience and members, students, professors, and speakers today for being patient and cooperating in this activity. So I announce a formal closure of this session. Thank you.
Thank you very much, and I appreciate your time and patience also, and I appreciate the questions, and I will also appreciate that if you can combinedly send all the questions to Vivek sir, and he will forward, and I'll definitely all the questions answer one by one, and I will forward to him.
Thank you. Thank you,
Thank
everyone.
you,
Have
sir.
a
Thank
good
you, sir.
day.
Everyone. Thank you, everyone.
So,